So I've just got the head from a Rexroth load sensing pressure limiting compensated variable piston pump, axial piston pump, and I just wanted to make an addendum to the video I made showing the controls, the DFR, the load sense pressure limiting compensator control that is typical on load sensing versions of modern heavy equipment systems. And of course I've got the connection here where the X is in the casting for the load sense line that would come from a load sensing directional control valve on a machine and feed into the pump. And it went through the operation of the spools and how they're going to control the swash plate angle in the pump in the other video. And I've got the swash plate out of this pump here. We'll talk about how that physically is going to get controlled within the pump. So I've got some connections marked where this is cut away and connects to the porting on the head of the pump. A, of course, is going to be where we're going to sense the pressure at the bottom of both the pressure limiting compensator spool and the load sense spool or the margin spool. And that connection A, if we were to follow that down into the head of the pump, it actually just connects to the discharge passage. So off of the high pressure side, the discharge side of this pump assembly where the connection would fit on. If I follow it up inside that hole, there's a connection from here, from the high pressure discharge up to port A. And that's a continuous connection. It's just a drilling in there that's made into that discharge port. So whatever system pressure is always going to be sensed at the bottom of these two spools. And then if either of these spools move to a position to direct that oil in this chamber feeding B, B just drills into this, it's basically a dead-ended path into the control piston or the D-stroke piston. So if oil's fed in a connection from A to B, it's just going to push out that control piston, and of course the swash plate then that would sit on here. I'm just going to tip this down. Look at the teeter-totter effect of the swash plate. So if the swash plate's on here, normal pump startup, or if the pump is not operating, we got the swash plate at a fairly steep angle, maximum angle, and that's because of the bias spring pushing this swash plate to maximum angle. But if this control piston comes out, of course it's going to do a teeter-totter effect on the swash plate and flatten out the angle. The further that control piston comes out, the less angle there is on the swash plate, less displacement there is on the pump. So the operation really comes down to the position of this control piston or D-stroke piston, and if it comes out, we D-stroke the pump. If it retracts, we upstroke the pump. On the other side of the swash plate, we've got the bias spring and bias piston, and I've changed out the spring here to a much lighter one that I can use so I can compress it by hand. The spring or two springs that normally reside here would be much stronger. But we've got our control piston, and up on this top are our D-stroke piston, and then we've got the bias piston and spring here. And the bias piston and spring are also connected to system pressure. Not only does system pressure or discharge pressure feed A to feed into the controls, it also full-time goes behind this guide. And this guide for the bias piston is basically connected as well to discharge pressure. So pressure is always feeding in the guide, and it's always able to push on this effective area of this bias piston that's going to work with the bias spring to try and keep the swash plate at maximum angle. Now, the trick to this whole system is the difference in effective area. You've got the effective area of this circle, and of course down inside this stem, whatever the area totals up for that circle. That's the cross-sectional area, the effective area system pressure can push on to work with the bias spring to try and keep the swash plate completely upstroked. On the control piston or D-stroke piston, you can see there's a much larger area in there that when oil comes through this guide and out the end here and pushes in this cup-shaped piston, it's got this whole cross-sectional area of that circle down in there to work with. So you get this difference in effective area. So if you send the same pressure to both, Obviously this D-stroke piston is going to have much greater force. It doesn't have a spring helping it, but it doesn't need it. It's just got the effective area on its side. So again, those are the forces trying to control the swash plate. Bias spring and small area piston on the bottom here, the way I've positioned this, and then large effective area D-stroke piston on the top. To get this lined up to get that started. I'm not going to screw that in all the way. I'm just going to start it in. So, again, at startup, or standby, if this is feeding a closed center DCV, pressure is going to build here at A. It's going to build in pump discharge, be sensed at A, lift the load sense spool, feed B, and of course that's where the D-stroke piston is going to come out to flatten the swash plate to give us minimum flow rate or minimum displacement at standby. And the stop for how far this piston is going to travel on this particular pump model is this hole. We've got the drilling to feed the D-stroke piston, but once the cup of that piston starts to uncover that hole, then this kind of loses its tractive effort as the oil feeding the D-stroke piston then starts to dump out to pump case. So we've got basically a connection to case drain, and if you monitor case drain flow out of this pump when the pump de-strokes, you will see an increase in case drain flow, because as that starts to uncover that hole and acts effectively as a minimum angle stop as the pump de-strokes, then the oil will start to add to case drain flow. And that's basically, if you've got a closed center valve that's completely sealed and you're wondering, you know, this pump doesn't de-stroke to 0 degrees of angle, it's still got some angle, and you're wondering where that flow is going. Well, that's the answer. It's actually dumping out that hole and dumping out the case drain of the pump. The connections X here, so we've got covered A and B. A is sensing pressure, B is feeding the control piston or D-stroke piston, and then I've tagged a hole here with an X, sort of weathered tag here, and that's connecting a path from here back to this hole, which also dumps into the case drain. So the drain full time for the spring of the pressure limiting compensator is made into the pump case there. So I've got that tag wire just looped through. And then if the control piston or D-stroke piston needs to allow the oil out of there to upstroke the pump, as the oil returns in B and comes across the load sense spool, if the load sense spool returns down because we get a load sense signal pressure in here, pushes that spool down or to the left now, then that oil coming back in B as this piston moves back is going to push across here, across here, across here, and make that connection at that land around through to the case. So again, we get a little bit of burst of case drain flow when the pump's upstroking, and that piston heads for letting the swash plate go to maximum angle. So again, when the pump calls for upstroke, or the system calls for a pump upstroke increase in displacement, that swash plate has to tip back. The bias piston and spring are always trying to push the swash plate towards maximum angle, and the D-stroke piston or control piston is what's going to move the swash plate to minimum angle. So during an upstroke, when we quit sending oil behind this guide, that hole's going to close. That was controlling our minimum angle. And then as the pump's upstroking, the oil is being pushed out from behind that piston, or being let out here through to the case. So A, pressure sensing for both of these spools, B, to the control piston to de-stroke the pump, and then X is my tag showing case drain connection for both the spring on the pressure limiting compensator and the drain for load sense control. Now the pressure limiting compensator, of course, can do the same thing. If pressure at A gets too high, thousands of psi, pressure limiting compensator can move over and control our high pressure cutoff and let oil bypass at this land right from A to B. And same thing that happens in load sense when you're de-stroking the pump will happen when the pressure limiting compensator decides it's time to de-stroke the pump. It'll just push that same control piston or de-stroke piston out, de-stroke the pump, and again we've got that hole controlling our stop position. And then when the pressure drops back down and that spool returns to the left or down, then again that oil can exhaust through here, out to the case. Now some of these Rexroth pumps you'll see adjustments through the head here to physically control your minimum and maximum angle stops. And if you wanted to adjust those, I guess on a test stand externally, then you'd appreciate those threaded stops. This one doesn't have that. This one, if you wanted to change it, you would have to unscrew the guide here and shim underneath it to control where that hole sits in relation to the surface of the head. And same with this bias piston. This one has neither side has adjustments on it, but some of the pumps do. We've got a class getting out up above us here. That's all the noise, the chairs rattling. So again, just wanted to make an addendum to that other video showing how those connections from the control are physically made into the D-stroke piston, and how the bias piston and spring are also being fed pressure full time, as is port A on this control.